In the last lecture, we introduced the battery, a device that can hold a roughly constant potential difference across a conducting wire, even when electrons flow through it. This allows for a steady movement of electrons for long periods of time. If we are to put electrical components along our wire, we can send electrons through them at a steady rate. We also introduced a quantity known as the electric current, which is just the amount of charge flowing through a point on the circuit per second. But a lot of questions remain. So far, we've treated the battery as holding a roughly fixed potential difference across the circuit, which generates a current, at least until the battery runs out. But we haven't yet established how large this current is, or what even determines it. In this lecture, we will look into this more closely and see if we can figure out what the current depends on and how it relates to the potential difference. Let's start by thinking about the electric current in terms of the electrons themselves. So far, we've understood the electric current as the charge moving through a point over a period of time. We also established back in lecture 1 that each electron has a fixed amount of charge, equal to minus E, where E is the elementary charge. Now we have already established that the electric current is the same everywhere in our circuit, at least in a series circuit, when the potential difference is fixed. If this is the case, in our simple circuit, consisting of only a wire, we can say that the velocity of each electron must be the same on average. Now technically, it might vary a little in the battery itself, but at any point in the wire, it is fixed. Yes, each electron has some random motion, but overall, this must cancel out if the current is to stay constant. We call the average velocity of the electrons the drift velocity, Vd. I will note that we are only concerned with the velocity in the direction of the wire. In reality, electrons could be moving a little left and right also, but we ignore this here. Now let's think about how we can define the drift velocity. Let's consider an electron moving through a small chunk of our wire. This chunk of our wire has a length delta L and a small cross-sectional area A. The volume delta V will therefore be A times delta L. The drift velocity for each electron is simply the distance delta L moved along the wire, divided by the time taken to do so, delta T. Now technically, velocity is a vector, so we should write delta L hat here as well. But as the direction is obviously from the negative battery terminal to the positive, it's fine to just ignore this. But what about delta Q? Well, we can say that our conducting wire and all the other components in our circuit that contribute electrons have a density of 3 electrons. In other words, a number of conducting electrons per unit volume. Let's define the number density of electrons, denoted by a lowercase n, which is just the number of mobile electrons, capital N, per unit volume V. This is simply the number of electrons moving around our circuit divided by the volume they move through. In our chunk of wire, delta L, the number of electrons is just the number density n times the volume of the wire, delta V. As we've said, delta V is just delta L times the cross-sectional area A, so the number of electrons is n times delta L times A. As the charge of each electron is fixed, equal to minus E, the change in charge delta Q within delta V is just minus E times n times delta L times A. Now, if we return to our equation for the current I, we can substitute this in for delta Q. As Vd is delta L over delta T, we can rearrange to get delta T equals delta L over Vd. If we rearrange this, we can cancel out the delta L's to obtain the current I equals minus N times E times Vd times A. This is another really useful way of writing the electric current, as it allows us to relate it to the electrons themselves. If we compare our two formulas for the current, we can say that I equals delta Q over delta T is the macroscopic formula, understood in terms of the charge in coulombs, while I equals minus N times E times Vd times A is our microscopic formula, telling us how the current can be calculated by looking at the properties of electrons, i.e. the number density and the drift velocity. You'll notice that we get a minus sign in front of this formula, which again indicates how the current points in the opposite direction to the drift velocity. Sometimes people just ignore the minus sign and use the magnitude of this expression, but you should always remember that current moves in the opposite direction to electronic motion. The current conventionally points from the positive terminal on the battery to the negative. This formula is useful because it allows us to figure out the drift velocity of electrons. Individual electrons are very difficult to detect, and it's effectively impossible to look at how fast they are drifting. However, the electric current I can be measured easily by other means, as can the cross-sectional area A. We know that the charge E is a fixed constant as well. The number density of electrons N is trickier, but this can be found if you know what materials the wire and other electrical components are made from. Essentially, all these quantities can be found through other means, and VD can be calculated. I should also quickly note that, though the current is fixed everywhere in our loop, the drift velocity is not necessarily fixed, as it depends on the cross-sectional area A. So if one part of the circuit has a different area for the electrons to flow through, to maintain the same current, the drift velocity will change. More on this later. Let's now go back to our basic circuit. We've established that we have a roughly constant potential difference, and that the current is constant. But what is this current? What actually determines how fast the electrons will move through our wire? We know that they experience a force due to the potential difference from the battery, but what else affects their motion? Well, as we've already said, each electron is repelled by every other electron, so it can only really move at the same speed as those around it. But they are also attracted to the positively charged nuclei in the wire that stay fixed in position. Now technically, these are actually ions, as they include nuclei and the electrons that are not free to drift. As the free electrons move through the wire, they are constantly colliding with these nuclei and scattering, which randomizes their movement a fair bit. Now in copper, which is a very good conductor, the effect of this is relatively small, but in other materials, such as zinc, a much weaker conductor, electrons are scattered more. Therefore, for the same amount of voltage, the electrons move more slowly through the zinc wire than the copper wire. We therefore say that the zinc wire has a higher electrical resistance than the copper wire. We denote resistance with a capital R. The electrical resistance of a component is simply the ratio between the potential difference applied over it and the resulting current going through it. In other words, R equals V over I. This is known as Ohm's law, named after German physicist Georg Ohm, who measured how the current through a material varies as the potential difference varied. Interestingly, he found that the ratio of potential difference to current stayed approximately constant for most materials, as long as the temperature was kept fixed. He measured the resistance for a material by making plots of the potential difference versus the current. These are known as IV curves. Let's change our wire to something other than copper, which has a very low resistance. For a fixed temperature, for most materials, these plots would be approximately linear. There would be exceptions, usually for very large and very small voltages, which I haven't shown here, but generally, Ohm's law is very accurate. The electrical resistance is simply the gradient of this plot. We measure the resistance in ohms, denoted by the capital omega symbol, which are also equal to volts per amp. I should note briefly that the most accurate formula for the resistance is actually the derivative form, R equals dV by di. In some more advanced circuits, we will see nonlinear IV curves, and in this case, the total circuit resistance is simply the gradient of this curve. So the resistance is V over I for ohmic materials, and dV by di for non-ohmic materials. But anyway, this is a really neat discovery, as once we know the resistance of an electrical component, we can figure out what current through it will be, just from the voltage of the battery. This being said, the resistance does usually change with temperature. The reason for this is that at a higher temperature, nuclei within the wire tend to vibrate more. As a result, this can change how much they scatter the electrons through our wire, and therefore change the resistance of the material. We can see how the resistance varies with temperature by simply plotting IV curves for a range of different temperatures. Now, as we said in the last lecture, you should never build a circuit consisting of just a copper wire and a battery. The reason is because the resistance of a copper wire is very small, so even for small potentials, the electric current is going to be huge. We'll talk about energy and power in the next lecture, but to cut a long story short, a large current and small resistance generates a lot of heat. This process is known as short-circuiting, and is something you want to avoid at all costs. Anyway, as long as our battery isn't damaged, we can prevent short-circuiting here by putting a high resistance material between our anode and cathode. The first device we'll introduce to our circuit is a simple resistor, which we denote in our circuit diagram with a rectangle. So let's see how this affects the current in our circuit. Now technically, everything in our circuit has a resistance, including the resistor, the two wires connecting it, and even the battery itself, which has a small internal resistance that I've ignored up to this point. We want the total resistance of the entire circuit, which in a series circuit like this one is just the sum of the resistances of each component. Now usually, the resistance of the actual resistor is way larger than everything else, so it's tempting to just ignore all the other stuff. But in some cases, these small resistances matter, so it's worth keeping them in mind when doing these calculations. In this case, we'll just ignore them. So the current is simply the voltage divided by the resistance. If we vary the voltage, the current increases linearly. There's one more nuance we need to mention here when it comes to resistance. So far, we have just said that each component in our circuit has a resistance, and that this is just a fixed number. This is true, but there's a much more general way to think about it. Let's see what happens when we vary the size of our resistor. Firstly, if we increase its length, we find that the resistance will increase. This makes sense, as there is now more resistive material for the electrons to pass through. The reverse happens as we shorten the resistor. Secondly, if we increase the cross-sectional area of the resistor, we find that the resistance decreases. This also makes sense, as the electrons are now less closely packed together. The opposite happens if we decrease the area, of course. Resistance is therefore proportional to the resistor length, and inversely proportional to the cross-sectional area. To generalize resistance, therefore, we define the resistivity, which is the measure of how well a material resists the motion of electrons, independent of its length or cross-sectional area. We denote resistivity with the Greek letter ρ. The resistance for a wire or component is simply the resistivity times the length of the component divided by its cross-sectional area. The resistivity is a much more useful number than a resistance, because if we know the resistivity of a material, we can find the resistance of a component made from this material, no matter its size. The units of resistivity are ohm meters. On a side note, we should also mention that we can define a quantity known as a conductance, which is simply the inverse of the resistance. This is denoted by the symbol G, and is just 1 divided by R. The units of conductance are Siemens, equivalent to ohms to the -1. The conductivity is similarly 1 divided by the resistivity, and is denoted by the Greek letter sigma. Using our previous equation for resistivity, we can now show that the conductance is equal to the conductivity times the area divided by the length. The units of conductivity are therefore Siemens per meter. Now you might be thinking, what's the point of conductance and conductivity, as they don't really add anything to the physics we've already discussed. But we'll see later that when calculating the properties of more advanced electrical circuits, we have to deal with 1/R terms quite a lot, and the expressions can get very ugly very fast, so conductance can come in handy. Anyway, let's summarize the key points from this video. In a series circuit, the electrical current is constant, and equal to the change in charge over the change in time. We can also write current as minus the number density of electrons times E times the drift velocity times the cross-sectional area of our wire. This also means that the drift velocity of electrons is not necessarily fixed when the current is fixed, as it depends on the cross-sectional area. The resistance of an electrical component is a measure of how strongly it opposes the flow of current. It is generally written as R equals dV by dy, the gradient of the IV curve, but in many situations this is linear, so R equals V over I. The IV curve being linear is known as Ohm's law. In this formula, R is the total resistance, and in a series circuit, this is just the sum of the resistances of each component. The resistance of a component varies with temperature, but for a fixed temperature, it stays approximately constant. We find that the resistance also depends on the length and cross-sectional area of a component. Therefore, we define resistivity. The resistance of a component is equal to the resistivity of the material times the length divided by the cross-sectional area. Finally, the conductivity is the inverse of the resistivity, and the conductance is the inverse of the resistance. Now in this case, using our battery to send a current through a resistor isn't particularly useful. But understanding how different components resist the flow of electrons is essential to electronics. The next thing we want to understand is how all this relates to energy. While all this is happening, energy is being transferred from one part of the circuit to another. In the next lecture, we'll introduce a few more useful components to our circuit and look at electrical energy, power, and efficiency.